Good afternoon to all of you. Welcome for the second session of the day. So in this session, we'll have lecture on allowable bearing capacity of soil from plate load test and penetration tests. I invite Professor K.S. Deena from Cochin University of Science and Technology to deliver lecture on the topic. Please, madam.
Thank you, Professor Reddy. Shall I share?
Yeah, I'll stop sharing. Now you can share, madam.
Okay, thank you. So, good afternoon, one and all. Today, we'll be focusing on the field test. So, I think you have given a basic idea regarding Tersaghi's analysis to how to find out the bearing capacity using bearing capacity equations. What is the mechanism of the bearing capacity failure, and how to calculate the bearing capacity that is using the equation CNC plus half gamma B and gamma plus Q and Q. So this we said this is for the analysis for the strip footing. Then Tersaghi has extended it to square footing and circular footing. Here, the ultimate bearing capacity, we'll find it out for local shear as well as for the general shear failure. The condition based on which the equation is derived is for the general shear failure, case, and then he has extended it to local shear failure by introducing the term C dash, N dash, C dash, NC dash, NQ dash, N gamma dash, etc. There we have seen for relative density greater than 70, we take it as or phi value greater than 36 degree, we assume general shear failure, and for relative density less than 20 and F less than 28, we assume local shear failure. Now these are some of the factors affecting bearing capacity, we said. So last class we have seen this slide, but now I think you can appreciate it more with the help of this bearing capacity equations. So the type of soil, type of foundation, size of foundation, depth of foundation, shape of foundation, because we have derived it for different shapes also, and the relative density, cohesion and friction angle C and phi. The NC, NQ and gamma values depends on the C and phi values. So now the position of water table also is a factor. I hope you have discussed that in detail, all these things in details in the tomorrow's morning class. So just to give an idea, the equation effect of water table on bearing capacity. Yesterday there was a question asking regarding that. That's why I thought I just include that. The equation for ultimate bearing capacity by Terzaghi is developed based on the assumption that water table is located at a great depth. So if the water table is located close to the foundation, the equation needs modification. The effective surcharge is reduced. In this equation, this is the QNQ part is the effective surcharge, that is the soil above the base of the foundation is of concern. And here this is a factor which we derive from the elastic wedge portion. So in this portion, the soil below the ground foundation depth is matters. So accordingly, the changes we make with the position of the water table also. The effective surcharge is reduced, that is Q term is reduced as the effective weight below the water table is equal to the submerged unit weight. So we introduce some terms, 0.5 gamma B submerged and gamma submerged we have to consider here for this QNQ term, gamma B, half gamma B and gamma term 0.5. Here also QNQ term you have to consider submerged density. So I hope you have discussed this thing in detail. So now come to our topic. So the field strength is field strength tests are mainly standard penetration test, pressure meter test, weighing shear test, cone penetration test, or dynamic cone penetration test, etc. It is difficult to obtain undisturbed samples of coarse-grained soils for testing in the laboratory in all the time. Hence, empirical methods are used to assess bearing capacity using test data from field tests like SPT or CPT, plate load test, etc. The value, N value obtained obtained from this test then has to be implemented or corrected. Now this routine field test in foundation engineering is for finding out the bearing capacity of shallow foundations is normally standard penetration test which gives the N value, and cone penetration test, then plate bearing test, etc. Now the standard penetration test is actually an empirical strength test. In fact, it is a byproduct of sampling operation routinely conducted in all sites where samples for laboratory tests are collected at various depths along with the advancement of foot boring. So in fact, it is the brainchild of an enterprising foreman of the Raymond Concrete Piling Company in USA, who thought of keeping a record of the number of blows during drilling while on soil investigation proceeds. The result of the test expressed as the standard penetration resistance, or the N value, which is reliably correlated with a phi value of a cohesionless soil, and hence used as the strength parameter of the soil in the geotechnical foundation design. So you can see the schematic standard penetration test here. So it's normally used in cohesionless soil like sand, The sample we can obtain from desired depth, and it is the most commonly used test in India. Its assembly consists of mainly a split spoon sampler, that is the sampler where we take the sample, and the cutting shoe we have, and the split barrel is there. It's a split spoon sampler. It's normally the diameter is 38 millimeter, and the sampling length is around 76 millimeter. Now, this sampler we inserted into the ground in a borehole, and it's a cutting shoe you can see, and it's a drill rod, and an impact block is there, anvil is there, and a heavy hammer and a guided tube, a coupling cable. These are the main parts of this this test setup. The test consists in causing the sampling tube spoon or sampling spoon to penetrate the soil by dropping the hammer having a weight of around 650 kilonewton, 650 newton or 65 kilogram from a height of 75 centimeter. And there we count the number of blows for a penetration of 300 millimeter, which is designated as the N value. So in this test, the counts are taken in 3 consecutive 150 millimeter penetrations, and the sum of the numbers of blows for the last 2 150 millimeter penetration is taken as the N value. That is, the first 150 millimeter penetration, we take it as seating drive, and we won't count it for the proper N value. The result of the test, actually, it's correlated with the value of phi value of a questionless soil. Hence, we can use it as a strength parameter in the designs. So what this gives, it's actually an account of a work done by a hammer. This energy used for the work done by the hammer is used for shearing 30 centimeter of soil, and also the some portion for the compression of the connecting rod and some hammer losses. So put together, all the 3 put together, we have the energy MGH. So the components B and C, we have to standardize. The major things which involved in this is the length of the rod, then how the straightness of the rod. All those things will involve in this these 2 factors. So it is always necessary to standardize these 2 in a precise manner. So the value, N value, gives actually an idea of work done required for shearing a 30 centimeter of soil. So if we got a large N value, it is assumed that the soil is dense and it is a competent soil. Where if the N value we get is small one, then it's loose soil and it is supposed to be incompetent one. The major factors affecting this N value is the depth factor, that is the depth of borehole or the depth at which we are taking the soil sample, and the drainage conditions, also the relative density of the soil. When you consider the depth, at greater depth, we have overburden pressure, so that the overburden pressure will be large if we go for a greater depth. And the confining stress corresponding to this depth, it will be also be large. And the major principal stresses at failure will be large for a given soil, that is for a given phi value. So the observed N value, that the shearing resistance will be more at a higher depth due to the presence of the larger confining stress. So observed N value will be larger than what we expect. So if the depth is small, overburden pressure will also be small, and the confining stress will be low, and the major principal stress at failure will also be low. So the observed N value, we considered it as less than what we expect for a given phi value. Then another factor what we said is drainage condition. That is, if the rate of loading of soil is more than the rate at which the excess pore pressure dissipates, that means undrained condition. The load is applied in undrained condition, the strength is governed by the effective stress, which exists only for the fraction of the second. The observed N value will be affected by this effective stress, because it's a sudden, it's mainly it's drop hammer, hammer drops we are giving. So it's a sudden impact we are applying to the soil, and because of that, the pore water pressure changes. This change in the pore water pressure, creating an undrained condition, may definitely change the shear strength of the soil. So such N value obtained will be more. So we have to think of the effective stress in terms of effective stress. Another parameter is relative density. If that is angle of shear phi value in term. So if phi is large, definitely we'll get a large N value, and soil is dense, we can expect large N value. So similarly, small relative phi value and loose soil will produce small N value. So in general, we can say the observed N value depends on the competency of the soil, that is phi, and the relative density of the soil, and the depth at which the observations are being taken, and the drainage conditions, that is if the test is conducted for a saturated condition or not. These relationships have been developed actually based on the past experience between the N value and the soil characteristics of phi and relative density. So these relationships may be used in the design. However, before using the observed values for the design, we have to make some corrections normally applied to the SPT blow counts to account for the, as I said, energy imparted, that is energy losses are there. So the energy imparted during the test, 60% of the hammer efficiency, the N value we calculate, and also the stress level at the test depth. For considering the stress level, we have to consider the overburden pressure. So we have to consider correction for overburden pressure, and again the dilatancy correction, water table correction, we have to apply for it. So coming to the correction for N value for overburden pressure, because low depth, as we said, shallow depths we underestimate the value of n, and at larger depth we overestimate. Therefore, we have to give some corrections to eliminate this effect of overburden pressure. We fix a standard pressure as 1 kilogram per centimeter square. That is the standard value we fix. Or here we have an equation for correction 0.77 is the IS code refers this equation. Cn correction n value is equal to 0.77 log 2000 to the base sigma overburden pressure, effective overburden pressure. So this equation is valid for an effective overburden pressure of pressure greater than or equal to 25 kilonewton per meter square. So here we have a plot which give correction factor and the effective overburden pressure. So we can use the chart directly, but normally this correction is not applied to the cohesive soil because its strength, cohesive soil strength mainly depends on the cohesion and not on the overburden pressure or phi value. So normally this method we won't adopt in cohesive soils. Then there is the next correction is the dilatancy correction, where in saturated fine sands and silt, this correction for dilatancy is done. Then where n value exceeds the 15, because the soil for in fine sands and silts, the permeability will be low, and the voids, saturated soils mean the voids will be filled with water. So it is it can create some effect on the n value, that is resistance offered. During shearing, this dense sand, normally dilatancy correction we applied on saturated dense silt sands. So this sands expands and due to dilation, and the voids are created in the soil mass. So these voids tries to suck water. Since permeability is low, this water does not enter these voids instantaneously. Again, we can go for the undrained condition. So because of this void and the low permeability, this void can create suction head within the soil mass. So negative pore pressure development will be there. That means the effective stress will increase. We know effective stress is equal to sigma minus U. So U becomes negative, means the effective stress increases. So that ultimately result in the increase in the strength. There's apparent increase in the strength for a fraction of a second. So the observed n value can be large. So this correction we apply is actually here, it is a negative correction we are applying. So this here, this again is not applied in clay soils. So the correction is when n value exceeds 50, we apply this correction, and n double dash is equal to 15 plus half of n dash minus 15. This n dash is the value corrected for overburden pressure. If that value corrected for overburden pressure is greater than 15, that amount the number count greater than 15 is reduced by half. So when n is 15, we put it like this, and n double dash will keep as n dash itself even n dash is less than 50. So n dash greater than 15 is an indication of dense soil. So in such soil, blows of drop hammer will cause increase in shear resistance. That is when n is greater than 50. As we explained earlier, this result in SPT value higher than the actual one. So, nutshell, first thing what we have to do is get observed n value from the field for a given depth, and if the soil is granular, apply overburden pressure, otherwise no correction, get n dash. Then apply the overburden pressure and get n dash. After getting n dash, again apply the saturated correction for dilatancy if the soil is saturated and fine sand or silt, and n dash is greater than 15, then apply dilatancy correction and get n double dash value. As all further design purposes, normally the n double dash is taken. Whenever you see n value, it is actually n double dash. So what is the use of getting this n value? Normally, the n value, once we get it, we can relate it with a phi value and the relative density. You can see here, if n is less than 4, it is related to, it's purely based on different analysis or different a huge number of test trials, what we do it in the field and do it in the lab, the same soil, and then the current correlation what we are getting. So when n is less than 4, normally we take it as 25 to 30 as the phi value, and relative density we put it as very poor soil, very loose soil. And 4 to 10, when n is 4 to 10, it is again relative density is also considered as low, and it is loose soil. Then 10 to 30, it's a medium soil, relative density of about 65. Medium soil, here we can go for some design purposes. Still, that depends on the load what we have to carry. So if the n value is greater than 30, that is n double dash is greater than 30, we can safely go for the constructions there. And we assume that the relative density is much high, 85%, and it is a dense soil, and 35 to 40, it's a phi value normally we consider. Then this is for a clay soil, but as we said, it's a classification for clay soil. But as we said earlier, this SPT test values are not directly will not be taken for the clay soils. When n value is less than 2, the UCC value, it is related to UCC value here, is less than 25, and the soil is supposed to be very soft soil. And 2 to 4, it is soft soil, and 4 to 8, it is medium. 8 to 16 in clay soil, the UCC value is somewhat stiff, that is 100 to 200 kPa. So we put it as stiff soil, and n value is greater than 16 to 32, it is very stiff, and greater than 32 value, n value, we found that the unconfined compressive strength is greater than 400 kPa, and it's a pretty good soil. It's hard soil. So in addition to these corrections, that is correction for dilatancy and correction for overburden pressure, As I said, there are so many losses which are coming during the process of SPT value, that is hammer blowing. So correction for hammer energy or efficiency of the hammer is also required. Then relative density and angle of shearing resistance of the granular soils using the penetration resistance in terms of N60 instead of N. That is, N60 means the normalized value at a geostatic vertical pressure of 1 bar by applying a coefficient Cn. So N60 is equal to N into Ce correction. The value corrected N for hammer efficiency is Ce. It's given as ER by 60. That is the energies of the different systems, say, vary from 45 to 98. So we have the equation N160 is equal to NCE N into CE, that is, we will see the values here, the nomenclature here. Sorry. N160, we will put it as N into CE into CN into CR into CV into CS, where CN is given by Skempton for fine sands as 2 by 1 plus sigma over vertical stress divided by 100, or it's given for an atmospheric pressure of 98.1. And Leo and Whitman has given this equation for finding the Cn at atmospheric pressure divided by the effective overburden pressure to the half. So here, the normalization at an effective stress of 100 kPa is again done. In this case, Kempton's case, and here Cn is the overburden correction factor, as we have already seen, and Ce is the energy correction factor, and Cr is the road length correction factor, and Cb is the borehole diameter correction factor, and Cs is the liner correction factor. Er is the hammer energy transfer ratio according to ASTM. Cn in practical application cannot exceed 2 and preferably not exceeding 1.5. So as we said earlier, these are the different parameters which create losses or affect the value of the N. So here we have a chart in which from which we can calculate or we can have an approximate range of all these correction factors. So Cn, we have already seen some equations for finding Cn. IS code equation is also there. Then for the energy loss, energy ratio Ce, accounting the energy loss, that depends on the type of hammer. Then it's different types: donut hammer, safety hammer, automatic trip donut hammer type. For different types, this correction factor Ce varies. It's 0.5 to 1, 0.7 to 1.2, 0.8 to 1.2, etc., 1.3, etc. So this this parameter Ce is equal to E percentage divided by 60. Now the borehole diameter, we normally take a borehole diameter as 150 to 200 millimeter the maximum, or 100 millimeter to 150 millimeter is the normal borehole what we do it in the field. So if the borehole diameter varies from that, what will be the change occur in N value? That is studied, and this table they obtained. So borehole diameter 65 to 115 millimeter, it is taken as 1 itself. 150 millimeter 1.05, 200 1.15. Then For rod length, it's again a measure of the depth at which we are taking the sample. If the rod length is less than 3, it is 0.75. It is 0.75. It is between 3 and 4, 0.8. 4 and 6, 0.85. 6 to 10, it is 0.95. 10 meter to 30 meter, it is taken as the standard value 1. So sampler again is creating the type of sampler is also creating the difference in the n value. If standard sampler is used, we put it as 1. Sampler without liner is 1.1 to 1.3. So these are the corrections, and this we have already seen the correlations between n. Here we have a chart which gives in the IS code that is standard penetration resistance versus angle of internal friction. So this is the very useful thing. From here, its chart is given in the IS code also. From here we can see for corresponding to different n values, we can correlate somehow the value of phi, angle of shearing resistance, and once we get the value of phi, we have NC, NQ, N gamma values we can directly chart out. So we can theoretically calculate what is the bearing capacity from this standard penetration value in an indirect way, that is relating to phi value and then relating to Terzaghi's or Neuhaus equations to find out the n value. Here, this is SPT value for cohesive soils. N is here. QU, unconfined compressive strength, is related to the n value as n divided by 0.075 kilonewton per meter square. Based on this chart is prepared. It may be noted that in place of a sample of height 100 millimeter for conducting the unconfined compressive test, we need to cause a penetration of 450 millimeter of the sampling tube for standard penetration test. So instead of considering 100 millimeter, here we are considering 450 millimeter of the sampling tube. 450 millimeter of the sampling tube for the standard penetration test. This means while unconfined compression test can locate weak spots, the standard penetration test average out the results over much greater depth. So the unconfined compressive strength is giving a localized value of the strength, whereas the n value, based on n value, if you are calculating it, it is giving a more or less average for a region of, say, around 40-45 centimeter. Now the empirical equations based on SPT values for footings on cohesionless soil. So this is the equation developed by Teng. Actually, the footing on granular soils are sometimes proportioned using empirical relationships. This Teng in 1969 proposed this an equation for a settlement of 25 millimeter based on the curves developed by Terzaghi and Peck in 1948. He modified this equation suggested by the Terzaghi and Peck and obtained this equation as QS is equal to 35 into n corrected minus 3 into b plus 0.3 by 2b the whole squared RW2 FD Kn kilonewton per meter square. So this unit is very much important because this equation holds good only if you are using or stick on to this equation is unit. So N CU corrected is the corrected standard penetration value. Then R is the RW2 is the water table correction factor, and FD is the depth factor, which is we normally take it as D plus DF by B, which is actually less than 2. Okay. B is the width of the footing in meters, DF is the depth of foundation in meters. Then Meyerhoff suggested this equation 1956 as QS is equal to 12 n corrected RW2FD for B less than or equal to 1.2 meter and for B greater than 1.2 meter, he put it as 8 n corrected B plus 0.3 by B the whole square RW2FD, where FD is given as 1 plus 0.33 DF divided by B, and FD should be less than or equal to 1.33. So the empirical model, this relations are still modifying and still research are going on in this direction. So the experimental results indicate that equations presented by Teng and Meyerhoff are too conservative. Then Bowles has modified this Teng's equation in 1996 and proposes an approximate increase of 50% over that of Meyerhoff, which can also be applied to Teng's equation. So the modified Teng's and Meyerhoff's equations are given like this. QS is equal to F3 n 53 n corrected minus 3 B plus 0.3 by 2B the whole square multiplied by the water table correction factor and the depth correction factor. And the Meyerhoff's equation is modified as QS is equal to 20 n corrected RW2 FD for B less than or equal to 1.2 meter. And for B greater than 1.2 meter, it is 12.5 n corrected B plus 0.3 by B the whole square. This QS gives the tolerable settlement, that is allowable settlement based on allowable settlement. If the tolerable settlement is greater than 25 millimeter, the safe bearing pressure computed by the equation can be increased linearly as S divided by 2.5 into QS, 25 into QS, where S is the settlement observed. That is for a net safe bearing pressure. We will find it. Net safe bearing pressure for a settlement of allowable settlement of say S dash. For 25 he has calculated, then correspondingly a linear increase he has given. Now coming to the plate load test, that is a most useful test. It's more accurate and most useful test, but it also has some limitations that we will see. So the plate bearing test it's also called plate load test, is an elaborate field test conducted at a foundation site for determining the bearing capacity and settlement at the field itself, directly from the field values. Indian IS code 1888 gives the details of this plate load test, which prefer to use a plate of 300, minimum 300 millimeter size, can be maximum up to 750 millimeter, depending on the type of the soil. Normally, steel plate made of very stiff, rigid plate, placing on the top of a level surface, which is used to transfer the load to the soil under test. So the bottommost plate is in contact with the soil. The load can be applied to the plate either from a loaded platform, that is like a gravity loading, which transferred in stages through a hydraulic jack, using a hydraulic jack, or by a hydraulic jack as a reaction against steel truss, structural loading designed for the requisite capacity and anchored to the ground. In both cases, the load is measured by a proving ring. A proving ring is used to measure the load, and the vertical deformation of the test plate is measured by using dial gauges. Fixed, these dial gauges are fixed on an immovable platform, so that the measurement what we are getting is exclusively the settlement of the plate. So this is the arrangement. Both the loaded platform and the reaction loading, reaction press can be considered as providing the necessary support for the jack to react against it. So when using the jack, when we try to push it up, this load will try to transfer through this jack and through this plate. So since the action and reaction are equal in magnitude and opposite in direction, the action of jack is upward on loaded platform and the truss, and downwards on the test plate below. So in gravity loading, the jack can be looked upon as progressively transferring the dead load on the platform to the soil, and the maximum value of which is full dead weight of the soil itself. Since the platform will get lifted from its support at the stage, the jack alone being the entire load, it is necessary to load the platform with a load higher than the estimated bearing capacity by a comfortable margin. In the same way, the truss must be designated for the same higher load acting upward and the reactions acting downward. Now, how to get the results from this? The data from this test is plotted in the form of a load settlement curve, both quantities being plotted in arithmetical scale. The determination of bearing capacity when curve is of this shape is a direct manner. I mean, we can directly find out However, if the load settlement diagram has the, if it is having the shape of this one, the second one, the determination of bearing capacity lies some uncertainty, and we have to consider empirical methods for identifying the value of bearing capacity. Normally, what we do is we put two tangents, and the common point at which the tangents meet is given and taken as a bearing capacity load corresponding to that bearing capacity. So IS code recommends determination of safe bearing value, that is not ultimate bearing capacity, against the settlement of the plate, which is related to the permissible design value of settlement of the actual footing by the expression SF by SP is equal to BF into BP plus 0.3 divided by BP into BF plus 0.3 the whole square, where S is the settlement and B is the width. Then P refers test plate and F refers actual plate, actual footing. So F settlement of the footing, ratio of the settlement of the footing to ratio of the settlement of the plate is equal to BF into BP plus 0.3 by BP into BF plus 0.3 the whole square. That is how the effect of the plate is taken into account. So I'll just skip some slides. Before that, I would like to show you the just a minute. I'll come back just a minute. So some mix up in slides got.
Ma'am, PPT is not so.
Yeah. Just a minute. Can you see the PPT? Can you see it now?
Yeah, it is visible, madam.
Yeah. So this is actually, I just wanted to show you a photograph of a plate load test, what is happening there. So under
Yes,
the
ma'am.
plate,
Well,
so this is a circular plate which is put, and this is the hydraulic jack, and you can see the dial gauges also, which are connected to a firm platform. It's a road connection, road is there, disconnected. The dial gauges are connected. The several dial gauges are attached to the independent suspension system to record plate settlement with each increment of the jack settlements are measured. Actually, while doing the test, first we give a seating drive, and after giving a seating drive, we give the loads in increment. Normally, at least 1/10 of the expected maximum capacity of the soil we give as the load increments, and we gradually increase the load. That is, after giving the first load increment, we wait for minimum 1 hour, or the settlement, the rate of settlement is less than 0.2 millimeter per hour. That is, we have to wait at least 1 hour and to see that the settlement, the increment in settlement is less than 0.2 millimeter. If the settlement is more than that, we have to again wait till the rate of settlement reaches that value, and you have to maintain that the same load till our target is obtained. If that is obtained, we can increase the load by load increments, as I suggested. That is about 1/10 of the maximum expected load. Then repeat the process and till failure. That is normally, in normal cases of a general shear failure, as we said, it's a sudden failure. So there we can reach a level at which we cannot maintain we won't be able to maintain the load on the jack. At that time, we can see that the settlement dial gauges will be running fast, and you can get the shape in the downward direction, the shape of the load settlement curve in the downward direction. Now, the major disadvantage of this plate load test, actually, the first thing, it is a cumbersome test, and it requires a skilled manpower to evaluate, and it should be very carefully taken. The reading should be very carefully taken, and it is expensive also. When you compare the SPT value, it is SPT test. It is very expensive, and also the arrangements we have to make. All this arrangement, you have seen the photograph. All the arrangements we have to take. We have to see that the water will not create problem. The rain will not create problem. All such things we have to take into account while doing the test, plate load test. More than all those things, the major disadvantage is the size effect of the plate. We can't simply increase the size. That is, when you put a plate and apply a load on it, normally, if B is the size of the plate, the stresses corresponding to this will be transmitting to a depth of about, say, 2 times the width of the footing or width of the plate. So the stresses will be in this region, or the stress withstanding, that the soil withstanding this stress will be in this region only. So if there is any soft material below this layer, that will not create any effect on the result of this plate load test. So if you are using a small plate and if you are using a bigger plate, what you will get, the result will be different. If the actual or if you compare the plate size and the actual footing, the plate size may be 0.2 meter or 0.3 meter, whereas the plate, our actual footing may be say around 2 meter or 1.5 meter. So the depth, the soil which is taking place, which is responsible for supporting will be in this region only, whereas here in actual case, the soil which is taking place, which is in the action, will be in this region. So if there is a soft material here, the strength will not be the same as we expect from here. So that is the stress influence zone is the major concern when we use a plate load test. Otherwise, we can directly get the bearing capacity, and also if the depth at which what we want, we can put the plate. All those things are there. Apart from the difficulty in putting the setup and also the cost, this is the technical difficulty or the drawback when we use a plate load test. Okay. Have you familiar? Are you familiar with the settlements? These settlements are covered?
No, this will be covered tomorrow, madam.
Tomorrow. Okay. So I'll go back. Sorry, some mix up in the slides happened. Here comes the cone penetration test. It's another test. Normally, we do it for finding or get an assessment of the strength characteristics of the soil. So we have a cone having a resistance, tip resistance. We will measure. Resistance, cone resistance Q0 or tip resistance QR, the QT is the notations normally used. So it's a friction ratio is find out frictional resistance, that is sleeve friction, and QC, cone penetration test says it's FR is equal to Fs by Qc into 100. So these are some of the cone resistance penetration test results. You can see the tip resistance versus depth of penetration. And so this QU friction ratio, and it is correlated with the velocity, that is shear velocity, shear modulus. So this cone penetration stat is actually the static cone penetration test results. It's a relation between static cone penetration, angle of shearing, resistance, and standard penetration. And this is the static cone penetration. So this is a comparison between the comparison of phi value from SPT and STPT, CPT values. Just bear with me for 1 minute.
No.
Yeah, just a minute. I'm
Meanwhile, there is a question I'll try to address.
yeah. You can ask questions. I actually my file got mixed up.
No problem, no problem. There was a question
Hmm.
under what circumstances pile load test is mandatory.
Okay. Pile load test.
Plate load test is mandatory.
Plate load test, yeah. Plate load test is, it's if there is no other means to find out the bearing capacity. As I said earlier, the plate load test, these are the difficulties we are having. If no other methods is possible, we'll go for a plate load test. Normally, we for large places where say ground improvements methods are we are using. In such cases, what we do is we do a the trial section. We conduct a trial ground improvement section, and in that we do this plate load test. We conduct a trial ground improvement method, or we can take a trial section and do the ground improvement. Say, for example, for the sand piles we are putting. This trial section, we normally do the plate load test after doing the this ground improvement. I think that is the place which we cannot avoid such things. Okay. I think this is a dynamic cone penetration test, but we follow the static penetration test. So SPT here, the difference between the, shall I continue then? Shall I continue?
Yeah.
This dynamic cone penetration test, in some places, the borehole, it will be difficult to take. So a borehole was required in SPT, and also samples were taken. But in the case of dynamic cone penetration test, mainly, though it's conducted for supplementing the SPT, it's give you a rough idea about the subsoil strata. It is very quick compared to SPT test, and it is cheaper also. But it gives lesser information, and it is in some cases we cannot take samples in a very loose granular soils. We cannot take samples. In such cases, it is better to go for a dynamic cone penetration test. Here, a cone which has an apex angle of 60 degrees attached to the lower end of the drill road and is driven to the soil in the same way as giving 65 kilogram hammer weight with a drop height of 750 millimeter. Here, the blows required to cause a successive 15 centimeter penetration are continuously counted. The same procedure is the same way as in the case of SPT. Here, a 50 millimeter cone is preferred if we are not using bentonite slurry. And if bentonite slurry is using to maintain the borehole, we go for 65 millimeter cone. The apex angle is again 60 degree. The procedure is cone is attached to the drill rod, and a hammer of 65 kilogram is used. The free fall of 750 millimeter. This is an arrangement for DCPT. The number of blows required to cause 15 centimeter penetration is recorded. Test is stopped if refusal occurs. In the case of SPT also, I forgot to tell the term refusal. When the number of blows is greater than 50 for a transmit of 15 centimeter, that is for a driving 15 centimeter, if the number of blows is greater than 50, we say it is the refusal. That is the soil is so hard. Then for further proceeding the test, we have to use diamond drill bit. We have to change the drill bit, and diamond drill bit we have to use. Here also the refusal condition, 50 or more blows are required for 15 centimeter penetration, 100 blows for 30 centimeter penetration. 10 successive blows produce no penetration. After the test is over, the drill rods are withdrawn, leaving the cone behind the ground. So that is a thing. In each test, we need a cone. The cone will be left there in the ground. So this is a DCT test. How it is plotted. So number of blows required for 30 centimeter penetration at a given depth is noted as the dynamic cone resistance, and it is denoted as NCD. The values are plotted against the depth. Generally, it is used to supplement SPT and not for design in isolation. Its alone is not taken. NCD is a measure of energy required for 30 centimeter penetration, as in the case of SPT. Large NCD is a competence stratum, small NCD it is soft stratum. The values should also be increased gradually with the depth due to overburden. So sudden change in NCD value made due to the change in stratum. So increase stiffer stratum, it will increase maybe due to the stone or boulder. Careful interpretation is required here also. Increase in NCD, decrease in NCD shows a soft pocket or a cavity. And that also we have to assess. We have to make our engineering judgment there. Now coming to the advantages of DCPT, it is a quick test and can cover large area under investigation economically. It helps in identifying uniformity of variability of the subsoil strata. It can be used to identify the soft pockets. If conducted at few points, the rock strata can also be located. And it can be used as a starting point for the investigation of a program. If tests are carried out close to a few boreholes where SPT data is available, a rough relationship between N and NCD results can be obtained. And after that, if you continue with the DCPT results or tests, a correlation can be done with the SPT value. Approximately, this is for a 50 mm cone. This is a general, it's a very approximate one. NCD is equal to approximately 1.5 times N for depth up to 3 meter and 1.75 times N for depth up to 3 to 6 meter. 2N for depth greater than 6 meter. So CBRI Roorkee, they have arrived at for 65 mm cone, CB 1.5 times the N value for depth less than 4 meter and 1.75 N value for depth between 4 and 9 and 2 for depth greater than 9 meters. Some small change between the limiting values. Now coming to the static cone penetration test, being used for soft clay sills and fine to medium sand deposits. It was developed in Holland and is also known as Dutch cone test. No borehole is also, it is here also it is not required. Here we have a sounding rod, a mantle tube and a friction jacket. Then normally apex angle of 60 degrees used with a base area of 10 centimeter square. So cone assembly. So this is a operation. The first thing, cone assembly and friction jacket assembly are put in the place, in a stationary place. Then cone is pushed into the soil. Cone is pushed into the soil by inner surrounding road to a depth of say A at a steady rate of 20 millimeter per second till a collar engages the cone. The force QC is read on a pressure gauge. Tip point or cone resistance QC is given by capital QC by AC. AC is the base area. Normally, this distance is about 4 centimeter. Then, sounding rod is pushed further to the depth for about 40 millimeter, and friction jacket and cone assembly are pushed together. So here QF is equal to F into S, force required to push the friction jacket as area of friction jacket. AF is the friction jacket and Fs is the side friction. So total Q is equal to QF plus QC, that is cone resistance plus frictional resistance along the surface. So total QF is equal to Q minus QC. So this is the major advantage of the this static cone penetration test, because here we can get an idea of what is the frictional resistance along the surface. The outside mantle tube is pushed by distance, say A plus B, and bringing the cone and friction jacket to position 1. So here, initially what we do is we push down the cone alone, and then the cone and the jacket together we push. So we can have, in the first case, we can get the tip resistance, and the second case, both the tip as well as the frictional resistance along the surface we will get. The difference we can, from the difference we can calculate what is the frictional resistance along the surface of the cone. So I think I covered most of the portions which is intended. So in general, we field test, most common is standard penetration test, and after that we can think of the this dynamic cone penetration test. Dynamic cone penetration test. This dynamic cone penetration test for the initial reconnaissance survey as well as initial idea we'll get, which is much cheaper than the static penetration test. This standard penetration test, where we can collect the soil samples and get more details regarding the soil samples at greater depths. So plate load test, wherever it is necessary. That is another thing is, if the strata is more or less uniform, it's okay that we can go for a plate load test. If the strata is not so uniform, then this major problem comes because of the size effects on the pressure bulb effect. That's what I can share with you. Any queries? If I can answer, I'm happy to do that.
So any questions are there from participants? So I would like to add one more thing regarding the plate load test, particularly in refusal strata. when you are doing a SPT test and you have encountered right a refusal condition. In such a case also, arriving at the exact allowable bearing capacity is difficult. So in such a case, right, if refusal strata is at shallow depth and if you are going for shallow foundation, the best way of determining allowable bearing capacity is to perform plate load test. Similarly, if you have coarse, gravelly soil, there also, right, you will see refusal in SPT test. So there also, after ensuring that refusal strata is continuous, then you can do plate load test and adopt reasonably good allowable bearing capacity. And as Madam told, for usage of reinforced soil bed and all, we can do the test on few layers of reinforced soil bed, and you can use it to a larger scale to support real footings.
That's it. Normally, we consider a small region of the soil to be improved, and we do whatever necessary improvement, method of improvement, we use it. We do it there according to the specification and see whether the actual capacity of the soil is achieved. To do that, sometimes we will go for the plate load test, because most of the region is almost uniform. The region under consideration is almost uniform. I think that is one way of doing it.
Yeah, particularly those sands if you are planning to densify with compaction piles.
Yeah, compaction.
Then the densification effect you can always measure through plate load test.
Plate load test, yeah.
So, thank you, Madam, for covering.
I am sorry that some disturbance came in between because it's unexpected. I could not open the actual file. That's why.
Okay. No issue, Madam. But still, you have covered all the field tests in a detailed manner. Coming to the penetration tests. Most of the application will be in case of deep foundations where we need soil properties to a larger depth, because these static cone penetration, dynamic cone penetration tests provide soil resistance data to continuous soil resistance data to greater depths. They will be of very much use in estimating load capacity of piles and all. So as Bina Madam told, as far as shallow foundations are concerned, you can base on SPT test. The thing is, the split spoon sampler to be used in the field should be of standard specifications. Hammer, whatever hammer you are using, whatever drop is specified. So in the field, you should ensure that all are properly followed by the agency who is doing the test, and corrections, whatever are required for N, they are to be done. Okay.
So thank you, on and all, for your patient listening and participation. And I also thank Professor Reddy for giving me this opportunity to interact with you people. So thank you so much.
Thank you, Madam, for sparing your time yesterday and today.
Thank you
for delivering two informative lectures. You have explained the things in a detailed manner. And whenever, one more thing I would like to say, whenever someone is planning for plate load test, try to do the test with using your test plate of larger size instead of going for small size, so as to have a reasonable estimate of soil. Because if you are going for 60 by 60 or 75 by 75, you will be exploring the load settlement behavior of soil extending to deeper depth instead of going for small size plate.
But there is a problem. That's actually I forgot to tell that, because when as we increase the size of the plate, the loading arrangements should
No,
also
No,
increase.
these
That is
days,
costly.
no,
That is
these days people are going for loading piles. They are doing pile load tests using like concrete blocks they are keeping,
Yeah.
and they are able to load up to even 500 tons also.
Yeah.
So that limitation has gone. Initial days that was given. Now people can comfortably do load tests on
That's true. Yeah.
using larger size plates.
But again,
Much more realistic.
the costs will be more than that.
Cost, no problem, madam. If it is a large project, they should be able to
Yeah.
pitch. Because wherever they are using piles, they are doing initial tests, routine tests. So they are happy that at least they are managing with shallow foundation due to availability of good soil. They should arrive at reasonably good value of allowed bearing capacity. So earlier days, going beyond a certain limit in terms of kinkage loading was problem. Now people are comfortably doing load tests. So anyway, what I mean to say is need not necessarily go for very large size, but instead of going for minimum 30 by 30, at least think of 45 by 45 or 60 by 60.
60.
60 by 60 will be reasonably good.
Yeah.
Does not cost much in creating your kinkage for loading. Right, and at the same time, it will give some reasonably good values. So thank you, madam.
Thank you. Thank you so much.
For your support for this.
Thank you. It's a pleasure. It's a pleasure to work with you. Thank
Yeah.
you.
We look forward for your continuous support and interaction with us.
Sure.
Thank you, madam. So I thank all the participants for their active participation in today's sessions. Hope you have enjoyed and gained certainly some new information in the topics of presentation. We'll be meeting again tomorrow at 9 a.m. for the lecture by Professor G.V. Rao. He will be covering the topic of settlement analysis of foundations, right? So be on time. We'll start session sharply at 9 o'clock in the morning. So thank you all. Bye for now. Thank you, madam, once again.
Thank you.
So before leaving, please ensure that you have submitted the attendance form. So if any of you have missed submitting attendance for the morning session, you can put a request so that Teja will send the link privately to you.